Hello, welcome back to the another reading session, that is the part 4 reading session on broadband silicon photonic directional coupler using asymmetric waveguide based phase control. So this is the abstract. Just for continuity purpose, let me read it. We designed and demonstrate broadband directional couplers that use asymmetric waveguide-based phase control section on the silicon on insulator platform. Broadband directional couplers with various power splitting ratios, including 10 is to 90, 20% to 80%, 30% to 70%, 40% to 60%, and 50% to 50%, were realized for both transverse electric and transverse magnetic modes. Some of the devices exhibit bandwidth in excess of 100 nanometer and all in excess of 75 nanometer. The footprints of the TE mode couplers are 32 micrometer into 1.3 micrometer or less, and those of the TM mode couplers are 13 micrometer into 1.3 micrometer or even less than that. So this is the main diagram which consists of two symmetric coupler separated by asymmetric waveguides. So symmetric couplers are 500 nanometer waveguide width and 220 nanometer waveguide height separated by 200 nanometer. Asymmetric section, which is also known as here phase control section, having waveguide width 600 nanometer and another one 400 nanometer separated by 300 nanometer. So this is the thing, and we have read in last part 3 section up to 3.2 fabrication and measurement. 3.1 we have read how this fabrication was done, and for the calibration purpose in this we can see one 3 dB Y branch is used, then imbalanced magazine interferometer, and this is the device under test that is called broadband directional coupler. And right hand side in figure C we can see here L1 L2 L1 the L1 are the symmetric waveguide, and L2 is the asymmetric waveguide. So we know here 200 nanometer separation, here 300 nanometer separation, 500 nanometer is the waveguide width, and 220 nanometer is the waveguide height. However, in asymmetric waveguide, we have 600 nanometer waveguide width. Another one is the 400 separated by 300 nanometer. In this height is common, that is the 220 nanometer. So and below section, this is the base is used only for the calibration purpose to assess the how much power is lost in the uh, grating couplers as well as Y branch. Now moving to coming on our section 3.3, which we have to start. Measurements of broadband directional couplers with other power splitting ratios. So this is the here figure, we can see figure number 8 is a measurement result for 10% to 90%, this one, and broadband directional coupler for TE and TM mode. So this is for TE sorry, and this is for TM mode. So on x-axis we have wavelength range from 1500 to 1600 nanometer in both cases. Then on y-axis we have normalized power splitting ratio. So power splitting ratio, it means here on one output is giving say 10% and other output is giving say 90%. So 10% has been assumed here. So you can say 0.1 is the normalized power. So this dark line of red color is the measurement, and this is the simulated one FDTD, that's the dash green. So simulated one, you can see it is giving say exactly 10%. However, when after fabrication, when it was taken actual measurement, then we can see this is the red color. It has little bit difference. Uh, it has little bit zigzag way with respect to each wavelength. So 1550, if we can see here, it is like that. However, we are concerned how much plus minus 1 dB. What is the bandwidth uh, or range of wavelength for which plus minus 1 dB uh, of point 0.1 and point 0.1 or 10% power is available. So that is the from 1580 nanometer to 1533. So almost. So here we can just subtract, you will get what is the bandwidth. So 13 minus 8, uh, 5, and here 8 minus 1, it is the 7. So 75 nanometer is the bandwidth of this. Similarly, we can get for this is for TE mode, and for TM mode we can see throughout from 1500 to 1600 nanometer means about say 193 basically exactly if you go. So 93 nanometer is the bandwidth for which plus minus 1 dB bandwidth is available for giving 10 is to 90% power splitting ratio for the light which is propagating in TM mode. So, and this figure 9 is 20 is to 80 for TE mode, and for TM mode is here. So all about it is how much bandwidth it is supporting. So large range of bandwidth you can see from 1512 to 1600 nanometer here, from 1500 to 87 for TM mode, for TE mode, and this 30 is to 70 for TE, and 30 is to 70 for TM mode. So you can see this is the plot normalized power splitting ratio versus wavelength, and this is the 40 is to 60. And here, this table basically summarizes all these numerical values. So average splitting ratio has been calculated here. So it was designed for 10 to 90%, but actually average value is coming 11.45 to 88.55. So plus minus 1 dB bandwidth is 75 nanometer here, and 88 here, 94 here, and so, and for 60 40 is to 60, it is greater than 100 nanometer. And these are the length of symmetric waveguide, and this is asymmetric waveguide, and this is the footprint. That is also very important, how much size, how much area it covers, how much area this device covers on wafer. So first, all these are 1, 2, 3, 4, 5 configurations are for TE mode, and rest 5 for TM mode. So we can see more or less this footprint size is lesser for TM mode compared to TE mode. Okay. Now these three isolated data points were ignored when evaluating the bandwidth of the couplers. Accordingly, all of the couplers show bandwidth of more than 75 nanometer, with some of them having bandwidth in excess of 100 nanometer. The excess losses for all of the T and TM mode couplers are below 1 dB and 0.7 dB respectively. Means for TE mode 1 dB and for TM mode 0.7 dB, that is the excess loss. As discussed in the previous section, the higher excess loss of T mode coupler can be attributed to the sidewall roughness. Because of the sidewall roughness, uh, actually it happens like this. Instead of having waveguide like this, we have actual waveguide like this. So because of the sidewall roughness, the excess loss is there, and that is more there in 40E mode because of the light nature like this. However, for TM already at this area. Now, the extracted eta cross of all of the T mode couplers are found to be less uniform than those of the TM mode coupler that we have seen. Uniformity is less in for TE mode, however, uniformity is more in TM mode. That is why bandwidth is also more. The sidewall roughness due to lithography and etching of the silicon oscillator waveguide leads to scattering at the sidewalls. The scattering not only contribute to the waveguide loss but also results in the back reflection. The back reflection leads to random Fabry-Pérot effect inside our MJ die, changing the transmission intensity through each waveguide and introducing phase shift. When the light goes into the combiner with random amplitude and phase versus wavelength, the extension ratio of MJ die spectra will be non-uniform, as the T mode has higher overlap with the side walls of the waveguides. The T mode coupler, okay, as the T modes has higher overlap with the side walls of the okay waveguide, the T mode couplers suffers higher waveguide loss and back reflection. Thus, their spectra and power splitting ratio are more random. In contrast to TM mode, has lower overlap with the side walls of the waveguide, suffering lower waveguide loss and back reflection, and thus everything looks more uniform. A study of the waveguide loss and back reflection for the T and TM mode can be found in reference 21. We emphasize that the extension ratio and the power splitting ratio of the TE mode couplers would have been more uniform if the device has been fabricated using 193 optical projection lithography, which introduced much less sidewall roughness instead of using electron beam lithography. Okay, so optical projection lithography is another advanced technology compared to electron beam lithography, which reduces that sidewall roughness. Now, section 3.4. Discussion of measurement results. Throughout this work, the indirect measurement method was used in characterizing all of the hour couplers because it has several advantages when compared with the direct measurement method. Firstly, the indirect method is much less sensitive to ripples in response to the grating couplers than the measurement method. So, indirect method is less sensitive to ripples. According to 19, the ripples in the response to our TE mode and TM mode grating couplers are 0.3 dB and 0.15 dB respectively. These ripples vary from one grating coupler to another in the fabrication run, and thus they cannot be calibrated out. According to equation 7, an ideal 50-50 coupler provides infinite extension ratio in the MJ die spectra output as a result of influence of plus minus zero point 0.3 dB ripple on extension ratio of MJ die spectra are negligible. For an ideal 10% to 90% coupler which provides 6 dB extension ratio in the MZ-I outputs, the influence of the plus minus zero point 0.1 dB ripple on the 6 dB ER leads to only a splitting ratio deviation of plus minus 0.8% on a linear scale, which is acceptable. In comparison, when directly measuring an ideal 50-50 coupler, the influence of plus minus zero point 0.3 dB ripple would lead to a splitting ratio deviation of 3 plus minus 3.7% on a linear scale in the both outputs. This is even worse for directly measuring an ideal 10% 90% coupler, where the same ripple would cause a deviation of about plus minus 3.4% on a linear scale in its higher output power. Secondly, the insertion loss of our grating couplers are sensitive to fabrication variation, such as wafer thickness, non-uniformity, as the indirect measurement method does not depend on the absolute output power. It can provide accurate results. So that is the reason why indirect measurement method has been used. Now coming to conclusion. We have demonstrated broadband TE mode and TM mode directional coupler. Our couplers show large bandwidth of more than 75 nanometer and show excess loss of less than 1 dB. Our couplers have simple structure, compact footprints, and are easy to fabricate. Using our approach and the contour map shows in figure 3, arbitrary power splitting ratio can be realized by simply setting the lengths of the symmetric couplers L1 and the length of the phase control section L2. While here the demonstrated couplers are cladded by silicon dioxide Couplers with other cladding, including air cladding, can also be realized by using our approach presented in the section 2. As fundamental components in photonic integrated circuit, the demonstrated broadband diagonal couplers would likely find many applications in areas such as optical switching and wavelength division multiplexing, and in devices such as polarization splitter rotators and modulators. Acknowledgement. We acknowledge the financial support from the Natural Science and Engineering Research Council of Canada and SERC, particularly the Silicon Electronic Photonic Integrated Circuits (SIEPIC) program. The devices were fabricated by Richard Bosco at the University of Washington, WNF, part of the NSF and NNIN. Zeqin Lu appreciates the China Scholarship Council for the financial support of his PhD program. We would like to thank Miguel Gullion for his assistance with the optical images, and thank Michael Coverley, University of British Columbia, and Minglai Ma USB for discussions. We acknowledge CMC Microsystem, Numerical Solutions, and Mentor Graphics for the design software. So with this today in part 4, we concluded this very important article authored by Professor Lukas et al. Designing of broadband directional coupler, which is available in now our SciEpic PDK process design kit. So with this, thank you so much for attending this session. See you in next reading session of other article. Thank you.